Imagine standing on the deck of a futuristic research vessel. But instead of Earth's oceans, you're gazing out across a sea of liquid methane beneath a hazy orange sky. The horizon blurs into a thick, unearthly atmosphere, and the water, if we can even call it that, boils at a temperature so low it would flash freeze human skin in seconds. Now imagine this. A sleek, autonomous robotic explorer quietly slips into those alien waves. Its mission? To plunge into the unknown and uncover secrets that could change our understanding of life in the cosmos. Sounds like science fiction, right? But this isn't a scene from a movie. It's a vision NASA is actively building toward with its next-generation robot, designed specifically to survive and explore Titan's alien oceans. Titan, Saturn's largest moon, is one of the most intriguing worlds in our solar system. Larger than the planet Mercury, and cloaked in a thick, nitrogen-rich atmosphere, Titan is the only place beyond Earth known to have stable bodies of liquid on its surface. But unlike Earth's water-based lakes, Titan's seas are composed primarily of liquid methane and ethane, hydrocarbons that under Earth's conditions exist only as gases. These lakes and seas span hundreds of kilometers, some deeper than the Empire State Building is tall, and they're nestled in a landscape shaped by organic sands, cryovolcanoes, and icy mountains. It's an alien world that somehow feels eerily familiar, and that's precisely why it's so compelling. NASA's upcoming robotic explorer, currently in advanced conceptual design, is not just any robot. It's being engineered to dive, float, and navigate through Titan's cryogenic seas while enduring conditions that would destroy most terrestrial technology in moments. Picture a hybrid between a mini submarine and a scientific lab built with advanced materials that remain flexible and functional at -180 degrees Celsius. Engineers are developing a specialized hull out of cryo-resistant polymers and titanium alloys, materials that can endure both the extreme cold and the chemical onslaught of hydrocarbon liquids without becoming brittle or corroded. Inside the vehicle, there's a compact radioisotope thermoelectric generator, or RTG, which converts heat from decaying plutonium into electricity. This is the same type of power source that's kept spacecraft like Voyager and Curiosity running for decades. But on Titan, it does more than power sensors. It also keeps the entire system from freezing solid. The interior is designed like a miniature spaceship, with redundancies in every system. Navigation relies on a suite of sensors, including advanced inertial guidance, real-time sonar, and even a radar altimeter adapted from Earth's polar exploration gear. These tools allow the robot to build detailed three-dimensional maps of Titan's seafloor, mapping features like underwater ridges, cryogenic vents, and sediment layers that may hold clues to organic processes. What's particularly fascinating is that this robot will operate semi-autonomously. Because Titan is more than 1 billion kilometers from Earth, communication takes up to 90 minutes round trip. That means real-time control is impossible. Instead, the robot must be smart enough to make decisions on its own. It will analyze samples, identify points of interest, and avoid obstacles without waiting for instructions. To prepare for this, NASA is conducting rigorous Earth-based simulations in analog environments, like the hydrocarbon-rich pools of Alberta's tar sands and the frigid lakes of Antarctica. Each test refines the robot's onboard AI, ensuring it can adapt to the dynamic, unpredictable nature of Titan's seas. And it's not just about engineering a tough machine. It's about what that machine might find. Titan's environment is a natural laboratory for studying prebiotic chemistry, the complex interactions of organic molecules that may have given rise to life. Scientists believe that in Titan's dense atmosphere, ultraviolet light from the sun triggers chemical reactions that produce a wide range of organic compounds. These compounds fall like snow into the lakes, creating a dynamic ecosystem of chemistry. If our robot can sample these substances, if it can isolate, analyze, and transmit data from them, we might gain unprecedented insight into how life could emerge in environments radically different from Earth's. It's not about finding little green men. It's about understanding whether life is a universal phenomenon or a cosmic fluke. The roots of this mission stretch back decades. In 2005, the European Space Agency's Huygens probe landed on Titan, transmitting the first images from its icy plains. That single descent, lasting only a few hours, ignited global fascination. Then the Cassini spacecraft gave us years of flybys and remote sensing. It showed us coastlines, lakes, storm systems, and methane clouds. But Cassini couldn't land on water. It couldn't dive. It couldn't tell us what lies beneath those waves. This robot will. And so here we are at the edge of a new era. NASA's vision is bold: to send a submarine into an alien ocean, to explore a world that mirrors early Earth in some ways and defies it in others. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together, because somewhere in the silent depths of Titan's methane seas, answers await. And perhaps, just perhaps, echoes of life are calling across time and space, waiting for someone or something to finally listen. To understand why Titan's alien oceans hold such power over the imaginations of scientists and science fiction lovers alike, we need to take a step back and ask a deceptively simple question: what makes a world habitable? For decades, our definition of habitability was Earth-centric: liquid water, a mild temperature range, and a stable atmosphere. But Titan dares us to think differently. It offers a world where methane plays the role of water, where clouds are not made of vapor but hydrocarbons, and where entire weather systems form without a single drop of H2O. It's a planet-sized chemistry set operating on rules so alien that even our most advanced Earth-based laboratories can only mimic fragments of it. And that's precisely what makes Titan the most Earth-like body in our solar system, by being so incredibly different. Let's paint the scene. Titan's atmosphere is a dense haze, about 1.5 times thicker than Earth's. If you were standing on its surface, the sky would glow orange. The sun, nearly 1,500,000,000 kilometers away, would appear as a pale disk, barely brighter than a street lamp on a foggy night. Winds whip across the landscape at a few kilometers per hour, but their force is amplified by the thick air. Methane clouds occasionally gather and unleash downpours that carve river channels into the icy crust. These rivers flow not with water, but with hydrocarbons, methane and ethane, cutting through dunes of frozen organic materials. Beneath Titan's icy shell, many scientists believe a subsurface ocean of water and ammonia lurks, heated by tidal flexing from Saturn's gravitational pull. That's right, Titan may have not one, but two oceans, one above, made of methane, and one below made of salty water. This dual ocean system is why astrobiologists are obsessed with Titan. You see, methane and ethane are organic solvents. While they're not nearly as reactive as water, they can dissolve other organic compounds, and over millions of years they may act as a medium for exotic chemistry. Meanwhile, beneath the surface, the subsurface ocean could be more similar to Earth's oceans than anything else in the solar system. And that opens up possibilities for life, not as we know it, but as it could be, life that breathes hydrogen instead of oxygen, or metabolizes acetylene and methane the way organisms on Earth use sugars. In 2010, researchers at Cornell University proposed that hypothetical life on Titan might use cell membranes made of small hydrocarbon molecules like acrylonitrile, forming structures called azotosomes, stable and flexible in Titan's frigid environment and completely unlike anything on Earth. It's a mind-bending idea, life not based on water, but methane. NASA's robotic explorer, which is currently being considered under mission concepts like the Titan submarine and the Oceanus project, would be humanity's first attempt to directly test these radical hypotheses. The submarine isn't just equipped with cameras and sonar, it will carry miniature mass spectrometers, chromatography systems, and molecular analyzers. These instruments are designed to identify complex hydrocarbons, possible biosignatures, and the ratios of stable isotopes that hint at non-random, possibly biological processes. Imagine this: the robot surfaces in Kraken Mare, Titan's largest sea, named after the mythical sea monster, and samples a floating film of organic molecules. The onboard lab begins its work, heating samples just enough to analyze them without boiling away key compounds. It identifies something unexpected, a compound that shouldn't exist without a very specific set of conditions, something that hints at processes beyond chemistry, something closer to biology. And it doesn't stop there. The robotic sub can stay submerged for days at a time, navigating deep trenches and mysterious underwater ridges. Its acoustic sensors pick up strange reverberations. Could they be caused by cryovolcanic activity, submerged methane geysers, or sediment shifts from unknown geological processes? Each ping from the sonar reveals a hidden landscape no human has ever seen. Canyons, plateaus, maybe even the deep vent-like structures that on Earth teem with life despite their darkness and pressure. The robot's infrared camera peers through the gloom, capturing ghostly images of drifting particles, possibly complex organic snow that's been accumulating for eons. Every byte of data is stored, compressed and transmitted back through Titan's thick atmosphere to an orbiting relay satellite, then beamed across interplanetary space to Earth. This is not the kind of exploration you can do with a simple flyby, or even a lander. It requires endurance, it requires resilience. It requires a robot that can do what humans can't: live, think, and operate in a place where temperatures hover just above absolute zero, and sunlight is barely more than a rumor. And perhaps most importantly, it requires curiosity. Titan challenges just to redefine the boundary between chemistry and biology, between geology and oceanography, between science fiction and scientific fact. It asks us to look at a place where it rains methane and wonder if someone or something might be watching from beneath the waves. As NASA engineers perfect the robot's pressure seals, refine its buoyancy controls, and train its AI in artificial oceans on Earth, the dream of exploring Titan becomes less of a fantasy and more of a plan. Step by step, sensor by sensor, line of code by line of code, we are preparing to pierce the veil of one of the solar system's most elusive frontiers. We are preparing not just to observe, but to immerse ourselves in a place so alien it feels like another universe, yet so scientifically crucial that we can no longer ignore it. Let's time travel, not into the distant future, but just a few decades from now. Picture this: the year is 2047. The world is watching, hearts racing, as a signal arrives at mission control after a 90-minute interplanetary delay. The message is short, cryptic but historic. The Titan submarine, humanity's first robot to ever dive into the seas of another world, has completed its first descent into Kraken Mare. The vehicle, bobbing like a ghostly sentinel beneath a methane-black sky, slipped below the surface just hours earlier. Now it's alive with data, transmitting sonar maps, chemical readings, and haunting audio of alien waves lapping against its hull. Across Earth, scientists erupt in celebration. But they know the real work has just begun. To grasp the magnitude of such a moment, we need to explore the immense engineering odyssey behind it. This isn't just a story of technology. It's a saga of perseverance, adaptation, and humanity's relentless desire to know the unknown. Getting a submarine to Titan isn't as easy as strapping it to a rocket and pointing it at Saturn. The journey is a marathon. It begins with a heavy lift launch from Earth, likely aboard the Space Launch System or a next-generation interplanetary rocket. The craft must cruise for nearly 7 years through the vacuum of space, slingshotting around planets to gain speed, before finally reaching the outskirts of Saturn's orbit, nearly 1,500,000,000 kilometers from home. But Titan is not a gentle host. Its thick atmosphere and low gravity present both opportunities and hazards. A parachute-assisted entry is possible, but the submarine must be encased in a heat-shielded aerodynamic shell that survives the descent, navigates through turbulent weather systems, and eventually splashes down with precision into one of Titan's lakes. Imagine landing a school bus-sized capsule in the middle of a freezing Black Sea, on a world where the temperature is minus 180 degrees Celsius, and where the surface pressure is 50% greater than Earth's. There's no GPS, no global navigation system, and the only maps are decades old, created by Cassini's radar from hundreds of kilometers above. Once the capsule hits the liquid surface, it must jettison its shell, extend communication antennae, activate its RTG power systems, and begin autonomous calibration, all without human intervention. Then comes the moment that changes everything. The submarine disengages from its cradle and silently sinks beneath the methane waves. Lights flicker on. Sonar pulses through the darkness. The mission has truly begun. And what the sub might find beneath those murky seas, that's where the true mystery lies. Kraken Mare is vast, covering more than 400,000 square kilometers. Its depths may reach hundreds of meters, with unexplored trenches and complex bottom topography. The first dives will be cautious, guided by pre-programmed mission parameters. Maintain depth, avoid underwater currents, steer clear of sharp geological features. But as the sub learns, its missions will grow bolder. It may explore the borders between Kraken Mare and smaller seas like Ligeia Mare and Punga Mare, investigating the way Titan's methane cycle mirrors Earth's hydrological cycle. It might encounter the submerged mouths of hydrocarbon rivers, where sediment and dissolved compounds collect. Prime spots to look for prebiotic chemistry. The sub's chemical lab will be the heart of its scientific arsenal. There, it will test samples for molecular complexity, chain length, isotopic ratios, and reactive behavior under cryogenic conditions. It will look for repeating patterns in carbon-based molecules, which could suggest self-organization, one of the first steps toward life. And if it finds anomalies, if the ratios are off or if molecules behave in ways we don't expect, scientists may be faced with their most tantalizing question yet. Is this chemistry purely geological, or is it something more? Meanwhile, the sub will also search for environmental signatures. Just like how life on Earth alters its surroundings through oxygen production, methane emissions, or pH changes, alien life, if it exists, might leave chemical fingerprints in Titan's lakes, maybe even thermal ones. If hydrothermal vents exist below the methane ocean, their heat could create localized environments far warmer than the ambient surroundings, pockets of warmth and energy where complex chemistry could thrive. It's possible that such areas might resemble the environments around Earth's own deep-sea hydrothermal vents, which teem with life, despite being completely isolated from sunlight. But Titan's alien ocean is more than just a science target. It's a philosophical challenge. If we find no signs of life, even after such a monumental effort, it forces us to confront hard questions. Is life truly rare? Is Earth a cosmic miracle? Or have we simply not looked in the right way or in the right place? The search itself becomes the answer, a testament to our refusal to be satisfied with ignorance. On Titan, we seek not only life, but context, evidence that tells us whether life is a quirk of Earth or a cosmic inevitability. And all the while, back on Earth, millions watch. Students, scientists, dreamers, young engineers inspired by the idea that you can build a machine smart enough, tough enough, curious enough to survive an alien ocean. In classrooms, teachers talk about Titan the way they once talked about the Moon or Mars. Titan becomes not just a world, but a mirror, reflecting our deepest questions and boldest ambitions. And that's why this mission matters. It's not just about hydrocarbons or robot submarines. It's about asking if we are truly alone and daring to listen for the answer in the cold, distant hush of an alien sea. In the end, it may not be what the robot discovers beneath the alien seas of Titan, but what it inspires here on Earth that leaves the greatest mark on history. Imagine the moment, decades from now, when the final chapter of this mission is written. The submarine, weathered by years of exposure to liquid methane, its once gleaming instruments now coated in frost and hydrocarbons, transmits its final signal. Perhaps it's an image of alien rain falling into a black sea, of a distant Saturn hanging low in Titan's sky. Or perhaps it's a chemical report, identifying something inexplicable, something that challenges every assumption we've made about life, chemistry, and our place in the cosmos. The data may seem cold, sterile, just ones and zeros flying through deep space. But behind every number is the beating heart of a question humanity has asked for millennia. Are we alone? That's the power of this mission. It's not about flashy headlines or immediate answers. It's about building a foundation, layer by layer, for a new kind of exploration. One that doesn't just visit a world and snap a few pictures, but truly immerses in it. One that listens to the waves, analyzes the sediment, dives beneath the surface, and stays long enough to understand. It's a mission that teaches us patience in the face of mystery and reverence in the face of the unknown. Think back to the Voyager probes. Launched in the 1970s, they carried golden records, messages to the stars. But they also carried something else, our first true glimpses of the outer planets. They inspired generations to think bigger, to build better. Cassini did. The same for Saturn. Perseverance is doing the same for Mars. The Titan submarine will be our next torchbearer, lighting the path not just for space agencies, but for humanity itself. And this isn't science fiction anymore. Right now, behind the scenes, teams of engineers, chemists, programmers, and astrobiologists are working to make this dream real. They're running simulations in labs chilled to cryogenic temperatures. They're building miniature submersibles that dive into tanks of liquid hydrocarbons. They're training artificial intelligence systems to make decisions in total darkness, with no lifeline to Earth for hours. Every test, every failure, every breakthrough, it's all moving us one step closer to Kraken Mare. But perhaps the greatest impact of this mission won't be scientific. It will be human. It will be the child watching a live simulation of the submarine's dive, eyes wide with wonder, whispering, "I want to build one someday." It will be the philosopher questioning what life truly means if it can exist in a place so unlike Earth. It will be the biologist rethinking cellular structures, the chemist reimagining solvents, the artist painting Titan's golden horizon, all of us expanding what we thought was possible. And if this robotic explorer finds something that truly defies explanation, something organic, something patterned, something unmistakably structured in a way that screams design over randomness, then the implications ripple across every boundary we've ever drawn. Because if life can emerge on Titan in a world of freezing methane where sunlight barely shines, then life could be everywhere. On Europa, on Enceladus, in the clouds of Venus, in subsurface oceans of distant exoplanets. It means the universe may not be silent, just waiting to be understood in a different language. So what do we do with that possibility? We listen, we build, we explore, and most of all, we continue. Because the universe isn't just out there. It's in us, in our curiosity, in our refusal to accept we don't know as the final answer. The Titan submarine is more than a robot. It's a vessel for our collective wonder. It's the bridge between science and soul. So now, we ask you if this journey inspired you, if it made you feel just a little smaller in the best possible way, then join us in spreading this story. Like this video, share it with fellow explorers, and leave us a comment below. What would you want to discover beneath the alien waves of Titan? Would you dive into the methane seas to find something that changes everything? Because out there, in the silence of space, something may already be waiting, and we're getting closer every day.